Magnetism, an invisible force that has captivated humanity for centuries. It is the force that makes magnets stick to your fridge, powers electric motors, and even guides migratory birds. At its core, magnetism is a fundamental force of nature arising from the motion of electric charges. When electric charges move, they generate magnetic fields, invisible lines of force that surround the moving charges. The ancient Greeks were among the first to observe the mysterious properties of magnetite, a naturally occurring magnetic mineral. They noticed how pieces of magnetite would attract iron fillings, a phenomenon that puzzled and fascinated them. Centuries later, scientists like William Gilbert and Christian Ørsted made significant strides in understanding magnetism. Gilbert, who is often called the father of electricity and magnetism, proposed that Earth itself is a giant magnet. Ørsted, on the other hand, discovered the connection between electricity and magnetism, showing that an electric current can create a magnetic field. Today, we harness the power of magnetism in countless ways, from powering our homes to exploring the cosmos. As we get deeper into the quantum world, we continue to uncover the mysteries of magnetism, pushing the boundaries of technology and our understanding of the universe. Did you know that our planet Earth itself is a giant magnet? It is true. This incredible fact has fascinated scientists for centuries. Though the exact reason is not known, scientists are of the opinion that at the heart of our planet, a swirling superhot liquid metal core generates a powerful magnetic field. This magnetic field extends far beyond Earth's surface, forming a protective shield known as magnetosphere. The magnetosphere safeguards our planet from harmful solar radiation and charged particles. It deflects these particles, preventing them from reaching the Earth's atmosphere and damaging life. But the Earth's magnetic field is not static. It is constantly shifting and changing. Over millions of years, the magnetic poles can even flip, causing the north and the south poles to switch places. Understanding Earth's magnetic field is crucial for various fields, from navigation to space exploration. By studying this natural wonder, we can gain insights into the planet's history, its future, and its role in the cosmic dance. Over the years, as the scientists started getting deeper understanding of magnetism as a subject, they proposed different tools and techniques to either visualize or have a conceptual picture to explain the properties of magnets and the theory of magnetism itself. Scientists proposed a mechanism called magnetic field lines that are considered as a visual tool used to represent the direction and the strength of magnetic field. Magnetic field lines are imaginary lines. They do not physically exist, yet they are used to map out the path that a north pole of a compass would take if placed at a particular point in the field. The direction of the magnetic field lines always point from the north pole to the south pole of a magnet. The density of field lines indicate the strength of the magnetic field. Closer and dense lines indicate a stronger field. An interesting phenomenon to note is that whatever may be the arrangement of nearby magnets or magnetic materials, the magnetic field lines never intersect each other. By definition, a magnetic field is a region of space where a magnetic force can be detected. Magnetic field can be detected easily using a magnetic compass. Magnetic field is generated by moving electric charges like the flow of electrons in a wire or the spinning of electrons in an atom. Visualize a magnetic field lines as an invisible force field surrounding a magnet. To help us visualize this field, we use magnetic field lines. These lines represent the direction and the strength of the magnetic field at each point. The Biot-Savart law is a fundamental law in electromagnetism that allows us to calculate the magnetic field generated by a current-carrying wire. It is a complex equation that involves integrals, but it is crucial for understanding how electric currents create magnetic fields. In simpler terms, the Biot-Savart law tells us that the magnetic field at a point due to a current-carrying conductor is directly proportional to the magnitude of the current, the length of the wire, and inversely proportional to the square of the distance from the conductor. A fascinating aspect of electromagnetism is the equivalence between a bar magnet and a solenoid. Bar magnet is a magnet in the form of a bar, whereas solenoid is an electromagnet made up of a coil wrapped around a soft iron core. When the current flows through the coil of a solenoid, it produces a magnetic field strikingly similar to that of a bar magnet. This equivalence is rooted in the fundamental nature of magnetism, which arises from the motion of electric charges. The magnetic field inside a long, tightly wound solenoid is nearly uniform and parallel to the axis of the solenoid. The magnitude of this magnetic field is proportional to number of turns of the coil, magnitude of the current through the coil, permeability of core, and inversely proportional to the length of the solenoid. A magnetic dipole is a pair of equal and opposite magnetic poles separated by a small distance. It is essentially a tiny magnet with a north pole and a south pole. You can think of it as a miniature bar magnet. While it is a simplified model, it effectively captures the behavior of many magnetic objects from atoms to macroscopic magnets. When you place a dipole in a uniform magnetic field, it gains potential energy depending upon magnetic moment, magnetic strength, and the angle between magnetic field and the magnetic moment. The magnitude of the potential energy of a bar magnet when placed in a uniform magnetic field is proportional to magnetic moment, the magnetic field, and the cosine of the angle between them. On similar lines, the torque experienced by a bar magnet when placed in a uniform magnetic field is proportional to magnetic moment, magnetic field, and the length of the bar magnet and trigonometric sine of angle between them. Gauss's law for magnetism states that the net magnetic flux through any closed surface is zero. This law essentially implies that magnetic field lines always form closed loops without any beginning or end. It is a fundamental principle in electromagnetism that highlights the absence of isolated magnetic poles or magnetic monopoles. In simpler terms, it means that magnetic field lines are continuous loops and there are no sources or sinks of magnetic field. Mathematically, the law can be expressed in two different forms. In differential form, it is expressed as del dot B equal to 0, and in an integral form, it is expressed as surface integral of B dot ds equals 0. Whether it is a bar magnet or a horseshoe magnet, a magnet has always two distinct ends, the north pole and the south pole. Toroid is an electromagnet. There are no poles associated with it. The magnetic field created by the current through the coil resides within the central core itself, and the magnetic field lines have no chance to expose themselves out of the core, hence no poles present in the toroid. Magnetic poles are the regions where the magnetic force is the strongest. Magnetic poles exert force on each other similar to a behavior observed in electric charges. Like poles repel and unlike poles attract each other. Though the behavior is similar to how electric charges interact, there is a key difference. Electric charges can exist separately, but magnetic poles cannot be isolated from each other. They always exist in pairs. Magnetic field exerts a force on a moving charge or any magnetic material around. Between any two magnets, this force can be either attractive or repulsive depending on the orientation of the magnetic poles with respect to each other. When two magnets are brought close to each other, the magnetic field lines interact. In the case of unlike poles, the field lines connect, resulting in an attractive force. Conversely, in case of like poles, the field lines repel each other, leading to a repulsive force. Magnetic field has no effect on a stationary electric charge because stationary charge will not create any magnetic field around it. A moving charge creates its own magnetic field around it and that interacts with external magnetic field to produce a force on the charged particle. Mathematically, the magnetic force on a moving charge can be calculated using Lorentz law, which states that magnetic force is proportional to the charge and the cross product of magnetic vector with the magnetic field vector. The cross product in the equation indicates that magnetic force is perpendicular to both the velocity vector and the magnetic field vector. The direction of the magnetic force can be determined using the right-hand rule. If you point your forefinger in the direction of the magnetic field and your middle finger in the direction of the current, your thumb will point towards the direction of the force. You can visualize how electron traces the path in a uniform magnetic field. This is the physics principle utilized in the design and construction of electric motors. Magnetic materials are classified into many categories on the basis of their magnetic properties. Permanent magnets are materials that retain their magnetic properties for a long period of time, even for many years, without requiring any external magnetic field. This remarkable property arises from the alignment of tiny magnetic domains within the material. Some examples of permanent magnets are neodymium magnets, ferrite magnets, and alnico magnets. In these materials, the magnetic domains, which are the regions of aligned magnetic moments, are locked into place, making the magnet permanent. This alignment is often achieved through a process called magnetization, where a strong magnetic field is applied to the material. Permanent magnets have numerous applications in our daily lives. They are used in motors, generators, speakers, hard drives, and many other devices. They are also essential for scientific research, medical technology, and space exploration. Temporary magnets are those materials which exhibit magnetic properties only in the presence of an external magnetic field. Unlike permanent magnets, temporary magnets lose their magnetic properties when the external magnetic field is removed. This property is attributed to the fact that the magnetic domains in a temporary magnet are not locked into place and can easily realign themselves even at normal temperature. Some examples of material that can be temporarily magnetized are soft iron and steel. When a soft iron nail is brought near a magnet, its magnetic domain aligned with the external field, making the nail magnetic. However, once the magnet is removed, the domains return to the random orientation and the nail loses its magnetism. Temporary magnets are widely used in various applications such as electromagnets. Electromagnets consist of a coil of wire wrapped around a core of ferromagnetic materials like soft iron. When an electric current flows through the coil, it generates a magnetic field, temporarily magnetizing the core. By controlling the current, the strength and the direction of the magnetic field can be adjusted. Electromagnets have numerous applications, including lifting heavy objects, powering electric motors, and generating magnetic resonance imaging scans. Natural magnets are materials found in nature that exhibit magnetic properties. The most common natural magnet is magnetite, also known as lodestone. Magnetite is a naturally occurring iron oxide mineral that has been used for centuries. The ancient Greeks and Chinese were aware of its magnetic properties and used it for navigation and other purposes. The magnetic properties of magnetite arise from the alignment of iron atoms within its crystal structure. These aligned atoms create tiny magnetic domains that collectively give the mineral its magnetic properties. While natural magnets like magnetite are fascinating, they are often weaker and less consistent than artificial magnets. However, they played a crucial role in the early understanding of magnetism and paved the way for the development of modern magnetic technologies. Diamagnetic materials are substances that are weakly repelled by a magnetic field. This property arises from the pairing of electrons in their atoms. When an external magnetic field is applied, a small induced magnetic field is generated in the opposite direction, causing the material to be repelled. While diamagnetism is a property exhibited by all materials, it is often overshadowed by stronger magnetic effects like ferromagnetism and paramagnetism. However, under strong magnetic fields, diamagnetic materials can display some intriguing behaviors. Examples of diamagnetic materials include water, gold, silver, copper, bismuth, etc. One of the most striking demonstrations of diamagnetism is the levitation of superconductor. When the material is cooled below a certain temperature, a superconductor becomes perfectly diamagnetic, expelling all magnetic field lines from its interior. This phenomenon, known as Meissner effect, allows superconductors to levitate themselves above the magnet. Understanding diamagnetism is essential for various applications, including magnetic levitation, magnetic shielding, and the development of advanced materials with the tailored magnetic properties. Paramagnetic materials are substances that are easily attracted to a magnetic field. This property arises from the presence of unpaired electrons in their atoms. When an external magnetic field is applied, these unpaired electrons align themselves with the field, creating a net magnetic moment and attracting the material to the magnet. Examples of paramagnetic materials include aluminum, magnesium, oxygen, titanium, etc. The magnetic susceptibility of paramagnetic materials is generally small and decreases with increasing temperature. This is because the thermal energy tends to randomize the alignment of the unpaired electrons, reducing the net magnetic moment. While paramagnetism is a relatively weak effect, it plays a crucial role in various scientific and technological applications. For instance, paramagnetic substances are used as contrast agents in magnetic resonance imaging to enhance the visibility of specific tissues. Understanding paramagnetism is essential for developing advanced materials with tailored magnetic properties such as magnetic storage devices and sensors. Ferromagnetic materials are substances that exhibit strong magnetic properties. They are strongly attracted to magnetic fields and can retain their magnetization even after the external magnetic field is removed. Examples of ferromagnetic materials include iron, nickel, cobalt, certain alloys like alnico. When a ferromagnetic material is placed in an external magnetic field, its magnetic domains align with the field, creating a strong net magnetic moment. Even after the external field is removed, the domains remain partially aligned, making the material a permanent magnet. Ferromagnetic materials play a crucial role in various technological applications, including electric motors, generators, transformers, and magnetic storage devices. They are also used in magnetic resonance imaging and magnetic separation techniques. Antiferromagnetic materials are a class of materials where the magnetic moments of neighboring atoms align in an antiparallel manner. This means that the magnetic moments of adjacent atoms point in opposite directions, resulting in a net magnetization of zero. Examples of antiferromagnetic materials include manganese oxide, chromium oxide, nickel oxide, etc. In antiferromagnetic materials, the exchange interactions, which favors parallel alignment of spins, competes with a weaker interaction that favors antiparallel alignment. The balance between these two interactions determines the magnetic properties of the material. At low temperatures, the antiparallel alignment of spins is dominant, leading to a net magnetization of zero. As the temperature increases, thermal energy can disrupt the antiparallel alignment, causing a gradual decrease in the antiferromagnetic order. Antiferromagnetic materials have potential applications in various fields, including spintronic and data storage. Free magnetic materials are a class of materials where the magnetic moments of neighboring atoms align in an antiparallel manner similar to antiferromagnetic materials. However, unlike antiferromagnetic materials, the magnitudes of the magnetic components in ferromagnetic materials are unequal. This imbalance results in a net magnetization. Examples of ferromagnetic materials include ferrites and garnets. In ferromagnetic materials, the magnetic moments of different ions within the crystal lattice are aligned in opposite directions, but the magnitudes of these moments are different. This imbalance leads to a net magnetization, making ferromagnetic materials useful for various applications. One of the key properties of ferromagnetic materials is their high electrical resistivity. This makes them ideal for high-frequency applications such as microwave devices and antennas. Additionally, ferromagnetic materials exhibit a phenomenon known as magnetoresistance effect, where the electrical resistance of the material changes in response to an applied magnetic field. This effect is exploited in magnetic sensors and data storage devices. Here is a summary of 5 different types of magnetic materials. In diamagnetic materials, magnetic domain is oriented in the opposite direction to the magnetic field. In paramagnetic materials, magnetic domain is oriented in the parallel direction to the magnetic field. In ferromagnetic materials, magnetic domain is aligned parallel in magnetic domains. In ferromagnetic materials, magnetic domain is aligned antiparallel but not cancel. In antiferromagnetic materials, magnetic domain is aligned antiparallel in magnetic domains. Magnetic materials are very useful in our daily lives, powering countless devices and technologies. Let us explore some of the everyday applications of these remarkable materials. Some common examples in electronic devices are magnetic hard drives, which store data by magnetizing tiny regions on a disk. In speakers and microphones, electromagnets are used to convert electrical signals into sound waves and vice versa. Electric motors and generators rely on the interaction between magnetic fields and electric currents to convert energy from one form to another. Magnetic materials are extensively used in medical devices such as magnetic resonance imaging, also called MRI. Powerful magnets are used to create detailed images of the human body. Magnetic therapy devices are used to alleviate pain and inflammation. In transportation sector, electric motors, which rely on magnetic fields, power electric cars and trucks. Electrically levitated trains called maglev trains are high-speed trains that use magnetic levitation to reduce the friction and increase efficiency. Common examples in consumer electronics sector are magnetic compass, which is a simple yet essential tool for navigation. Refrigerator magnets are colorful, beautiful magnets that hold notes and photos. Magnetic door catches are used to keep doors closed securely. In industrial applications, magnetic separation techniques is used to separate materials based on their magnetic properties. Magnetic cranes are used in lifting heavy metal objects. As technology continues to advance, the applications of magnetic materials are also expanding. The field of materials science is constantly evolving, and advanced magnetic materials are at the forefront of technological innovation. These materials possess extraordinary properties that are pushing the boundaries of what is possible. High temperature superconductors exhibit zero electrical resistance below a certain critical temperature. The discovery of high temperature superconductors has opened up new possibilities for energy efficient technologies such as superconducting magnets for powerful particle accelerators and energy efficient power grids. Magnetic shape memory alloys can change the shape in response to a magnetic field. This property has applications in actuators, sensors, and biomedical devices. Spintronics is a field of research that exploits the spin of electrons in addition to the charge to develop new electronic devices. Spintronic devices promise faster, more energy efficient, and denser data storage and processing. Magnetic nanomaterials with unique magnetic properties are being developed for various applications, including targeted drug delivery, magnetic data storage, and catalysis. As the world seeks sustainable and efficient energy storage solutions, magnetic energy storage emerges as a promising technology. This innovative approach utilizes magnetic fields to store large amount of the energy. By passing a large electric current through a superconducting coil, a powerful magnetic field is generated. This magnetic field stores energy in the form of potential energy. When energy is needed, the magnetic field is reduced and the stored energy is released as electrical energy. These systems can deliver high power output, making them suitable for applications that require rapid energy delivery. Unlike batteries, magnetic energy storage systems can store energy for extended periods without significant energy loss. Magnetic storage systems can be charged and discharged rapidly, making them ideal for peak load sharing and grid stabilization. While magnetic energy storage technology is still in its early stage of development, it holds immense potential to revolutionize the energy landscape. A lot of research is being done in the field of magnetism and superconductivity. If a superconductor is placed in the magnetic field, it is observed that the external magnetic field lines do not pass through the superconductor. This phenomenon is known as Meissner effect. When a superconductor is cooled below its critical temperature, it expels magnetic field lines from its interior. This expulsion creates a perfect diamagnetic state where the magnetic field within the superconductor becomes zero. As a result, the superconductor acts as a perfect diamagnet, repelling external magnetic field. This property is exploited in various applications such as magnetic levitation. However, if a permanent magnet is cooled to a temperature below its superconducting transition temperature, it would not necessarily lose its magnetic properties. However, its behavior would be influenced by the superconducting state. Superconductivity and magnetism are often seen as opposing phenomena. Permanent magnets generate magnetic field, while superconductors tend to expel them. Magnetic properties are intrinsic to its atomic structure, so magnets will retain their magnetic properties even below superconducting transition temperature. But how they react with external magnetic field at the temperature is an interesting field for future research. When a magnet is cut transversely, each piece becomes a new smaller magnet with its own north and south poles. The pole strength of each new magnet remains the same as that of the original magnet. The magnetic moment of each new magnet is reduced as it is proportional to the length of the magnet. Even when cut along its length, each piece will still have both a north and a south pole. The pole strength of each new magnet is reduced compared to the original magnet. The magnetic moment of each new magnet is also reduced. With this, we have just covered the basics here. Remember, there is always more to learn. Thanks for joining me.